Welcome to Linear Electronics, Chapter 8. We're going to talk about filters in this chapter. Those are the sections to read. This chapter will discuss a plan to build active filters. We will touch some base on passive filters, and we'll start there. And what it is presented here is just a modest approach to a vast area of electrical engineering. Our approach is to classify filters simply as a device to pass certain frequencies and reject others. Now, if you got into imaging processing techniques, that's way outside the frequency domain, which is more complex and outside the boundaries of this discussion. Let's first define an active and passive filter. Passive filters, they've been around a long time. Active filters, they still use some passive components like a capacitor and resistor, and one or more active device. And in our situation, we're going to use op amps. And we also want to be aware of the advantages and disadvantages of both techniques. An RLC, or passive approach, they use devices which might be considered maybe imperfect with large tolerances. They can get into large physical size depending on the frequency range you're working in, and the cost can be a factor. And getting the values at certain values, specific values, is difficult on some devices, such as inductors and capacitors. Some frequencies are better suited for passive devices, and that hasn't changed. Low and very low frequency spectrum is better suited, though, for active filters, and more that's becoming common. However, passive filters are still dominant if we get into the radio frequency range. Some of the disadvantages and advantages of passive filters, specifically with the use of inductors, are presented here. Inductors, they can radiate interference. They can be large in size. They can, increasingly though, the active circuits are used to replace inductors in circuits. At low frequencies, inductors used in passive filters will require big cores, and the devices at that point become large, and they cause interference, and they're expensive, and they can just be generally inaccurate. Active filters are considered generally to be used at low frequencies, which with a limit maybe up to 100 kilohertz. However, experience is the best teacher on the type of filter to use, either active or passive. Any type of active device requires consistent, clean power to maintain the system. Active devices do fail more often than passive devices, which are more rugged. Passive devices are more rugged, and they can withstand voltage changes better, and they can operate within inconsistent operational power. Active filters are gaining popularity, though, and remember the upper frequency range or limit is around 100 kilohertz. A couple of terms to understand is the stop band. That's the range of frequencies that we should greatly limit or attenuate. And then the pass band is the range of frequencies that should be allowed through the filter. And some also add the transition band, which is the range of frequencies between both the pass band and the stop bands. We'll concentrate mainly here on low pass and high pass filters. I will identify a couple other types of filters, but we're going to go through discussing mostly really low pass filters. An ideal low pass filter is shown with the amplitude, the frequency band, and the cutoff frequency. So here's our cutoff frequency right here, and here's the frequency it's allowed to pass through. This is the frequency on this axis and the amplitude. So all frequencies lower than the cutoff frequency are allowed to pass through, but frequencies that are higher than F sub C are rejected. An ideal, this is a high pass filter, rejects frequency below the cutoff frequency, and it allows the frequencies to go through that are above F sub C. When describing a band pass filter, we introduce the center frequency. We use F sub O here because F sub C is the cutoff frequency. So this will be the center frequency. And we also introduce the word bandwidth. It's the difference between the upper and lower frequencies in a continuous set of frequencies. So for this filter, the bandwidth is a range of frequencies allowed to pass through the filter. This is called a bandpass filter. Now if we go to the band rejection filter, for this filter, the bandwidth is a range of frequencies not allowed to pass through the circuit. And we're all going around that center frequency. There is a difference between the ideal and the actual characteristics of the filter. This is not even really, this is kind of like an ideal look. This is very ideal. But we notice we have the pass band, the transition band, and the stop band. If you stick to a stringent set of specs, the circuit can be quite complex. But in most cases, this is not required. That accuracy level is not required. The design approach is to develop a filter that meets or exceeds the specification. What level of attenuation is required to do the job, and at what frequency should it be applied? At what frequency should we start attenuating the amplitude of that signal? And how big is that transition band? Is it very? Do we have to be very exact about this? Those are the kind of questions we have to ask when we're designing a filter. A popular method to design filters is to use a normalized circuit using basic components like just 1 ohm for resistors, 1 farad for caps. Now this is unrealistic, but it's a place to begin, and then from there we scale towards a workable component. There are 2 popular processes in scaling, either frequency or impedance scaling. When we use scaling, we don't change the capacitors and resistors proportionally because they are inverse proportional. When changing a capacitor, we change the resistor inverse proportionally. Always remember that. And this is best described when we do an example. If I look at the third bullet here, we're not going to do this, but it's good knowledge to have working in the filter domain. If all capacitor values in an RC active low-pass filter are halved, the cutoff frequency is doubled. The process of changing either the capacitance value or the resistance values may be used to shift the frequency range of an RC filter. The following are assumptions used when developing a filter. These designs will have a normalized 3 dB radian cutoff frequency, and the reference of our angular velocity is 1 radian per second. These principles will be better understood when we're doing an example. This is a passive filter with a cutoff frequency of 1 kilohertz, and we're starting to design it. We have this at 1 ohm and 1 farad, which isn't the final product. We desire a capacitor that will, and resistor value for a 3 dB attenuation break at 1 kilohertz. Notice we'll start with a normalized circuit, 1 ohm, and C equals 1 farad. And the first thing we're going to do, I have 3 things we're going to do here. The first thing is the frequency, is to find the frequency scaling constant. So I do that by taking 2 pi f, and this is our cutoff frequency we're going to use, 1k, and we're 2 pi times 1k, that's the angular velocity, and we're divided by 1, and that's just our scale value that we're starting with. And second, we're going to scale the capacitor value. We're going to take the normalized value divided by k sub f, which is what we just found. So we're going to take the 1 farad normalized value divided by 6.28k in this example, and we get a value that's in the microfarad range. So we're starting to get close to something that we can actually build and put together. However, we're going to identify, capacitors are hard to find as far as that value, so we're going to start off with a value that we know we can find. Resistors we can change very easily. So we want this value to be 0.001 microfarad. So what we're going to do is we're going to divide the value we came up with, 159 microfarad, divided by the value we want, and we get 159.24 K. And we're going to increase the value of the resistor now from 1 to 160 K. That's about what that is. And remember that capacitors and resistors are inverse proportional to each other. And so here's our final value. Let's look at our circuit here. Here's our final value, 160K, 0.001. Now we want to test this circuit and see how it works. We should be in the ballpark and we can start tweaking it from there. So I built this circuit in multisim, and I set up a function generator for a sine wave at 1 megahertz, way beyond that cutoff frequency. I want to see if it's going to cut it off. And I have 10 volts peak, and I'm using a Bodie plot device that's in multisim. And I noticed that the results identified at the circles, I used all default values here. I have about 3 dB is my cutoff range right here, and I have around 1 kilohertz, so it works. And then from there it continues to drop off till it eventually goes to 0. So we're going to go now to part 2 of this presentation. You can go to part 2 at your convenience, and we're going to really concentrate now on active filters in part 2. Thank you.